Good morning, curious minds. Welcome to another video on smart architectural programming. Today we're diving into the fascinating world of simulated annealing, a technique that sounds more like a fancy cooking method than an AI algorithm. But don't be fooled. It's not just about frying your circuits, it's about crafting smart, efficient solutions to complex problems. Are you ready to turn up the heat on your understanding of AI optimization? Then, without further ado, let's go. Before that, I would request you, if you got any value from this video, please like and subscribe. And then let's move on to what is simulated annealing. So let's start with the basics. Simulated annealing is the optimization algorithm inspired by the process of annealing in metallurgy. Metallurgy, yep, that's the art of heating metals and cooling them down slowly to remove imperfections. In the AI world, this translates to finding the best solution to the problem by exploring different possibilities and gradually focusing on the most optimal solution that you can find. Think of it like navigating a tricky maze with a flashlight that dims over time. You explore broadly at first and then you refine your path as you go along. Just a little bit of a tidbit at this stage. Remember, OpenAI is one of the most initial projects of OpenAI before ChatGPT was them creating these bots in, I think, World of Warcraft that were very, very effective in actually, fighting in an equal battle with world champions of World of Warcraft. And that particular AI was so successful, a major reason for behind that was simulated annealing. By this method, basically, the players that they set up initially, the AI basically, it first learned to walk. One player, the game took one step, but it moved forward and then it fell. It learned by continuous experiments how to walk first, and so on and so forth. So that is one of the major methods through which how AI actually basically learns to get the most optimized way to solve a problem, basically. So with that tidbit out of the way, let's move on to the next idea in this video. That is the big idea behind simulated annealing. So here's the deal. Controlled randomness. That's the concept that we need to understand. At the start of essay, which is I'm going to say essay for simulated annealing instead of repeating that over and over again. So SA acts a little reckless, basically. It tries all sorts of wild solutions, and this is something that you can understand from my previous reference to OpenAI's World of Warcraft AIs, basically. So what happens is, as I mentioned before, it tries to crawl instead of walking. It tries to jump instead of walking until it achieves what it's trying to do, moving from A to B, basically. So that's what it means by the essay as a little reckless. It tries all sort of wild solutions instead of having any preconceived notion of how to get from A to B. It tries everything out within the control parameters given to it, like that gaming character in World of Warcraft, and then basically identifies after trying everything out what is the best way from getting from A to B, basically. Why? Because when the temperature is high, the algorithm allows itself to make big jumps, even if these jumps lead to worse solutions. It's all part of the plan of the algorithm to find the optimized solution. As the temperature cools, the jumps get smaller and the algorithm becomes more focused, honing in on the best solution. It's like starting your problem-solving journey with a shotgun approach and ending with a laser precision. Pew pew. So with that, we can move on to the next section, which is where can we use simulated annealing. So this is not something that's completely focused towards only AI. You might wonder, why would I need this? Well, SA shines in situations where finding the best solution feels like searching for a needle in a haystack. Some of the most important concepts or uses for simulated annealing would exemplify this notion. So city planning and smart architecture. So generally speaking, people have these assumptions for centuries on how to plan a city, basically. They mark roads, they mark green belts, they mark parks, they mark housing areas, so on and so forth. All of this is based on a presumption of how things should go to make the traffic, work better. And over the years, this science was honed into what it is right now. But city planning is never very accurate. You cannot accurately map out how to best optimize road lanes, how to best optimize the ingress and egress of traffic, and how to best zone the areas and how to best place the parks, basically. But this can be done effectively using SA or simulated annealing. Need to arrange buildings, roads, or utilities for efficiency? SA can help you find the best layout while balancing aesthetics and functionality. How would it go about doing that, basically? So it would do that by a very simple aspect, right? So we set up an AI and tell him that, we need to design a housing area, we need to design a commercial area, we need to design a government office area, and we also need to design basically you could say we need to design the roads and making the ingress and egress of traffic more effective, and the road lanes more effective in reaching important areas from one area to the other. And then we tell the AI and to run a SA, basically a simulated annealing, and find the best solution for that, basically. And it would go through it over and over again from hot temperature when it's trying wild solutions with the least optimized answers, and then it would basically try solutions at low temperature, which will slowly get it to the most optimized solution. So that's how it can help in city planning and smart architecture. The second and aspect to simulated annealing is scheduling problems, basically. So again, ever tried organizing tasks, meeting, or resources without any headaches? SA can save day by day conflicts by minimizing conflicts and maximizing productivity. Again, you can basically train your AI to run essays on simulated annealing on different work schedules, basically, and train it to get the most optimized tasks situated next to each other. So instead of going to the city council to get a permit and then going to a meeting and then going back to the city council to apply for a new permit, basically, it would basically make sure that you're only you basically do the tasks that you can do collectively. So first you go to your meeting, and then you go and get the permit and apply for the new permit at the same time, basically. So that's how it can make optimizing tasks much more effective using simulated annealing in AI. Keep in mind, though, these are just simple examples that I'm using here. They're more complicated usages for this particular concept in problem scheduling as well. Then we have design optimization. So we have AI chip designs and we have structural engineering. Simulated annealing can refine designs for efficiency and performance. So let me give you this perspective, right? So in AI chips, AI chips or other chips, basically any chip like the processor in your computer right now, these chips are very, very small, like they're in nanometers, right? And their designs were previously designed by humans, but over the years they realized that the computer efficiency in designing these chips is much higher than humans, especially considering that we need to optimize for space much more effectively because these chips are getting smaller and smaller and smaller. So design optimization by trying different ideas led to these very, very efficient chips. And now we're using AI to run these simulated annealing, basically, instead of manual ways to do that, and we're getting very, very efficient chips being designed in the current day and era. And finally, the last focus for simulated annealing is the AI and machine learning. So it helps to tweak hyperparameters to find optimal configurations for models. It's like tuning guitar, hit the right note, and your AI sings beautifully. Let's break that down a little bit. So basically, an AI and machine learning is simply giving a huge amount of data to a particular computer or to a particular program, and that program goes over the data over and over again and find patterns, basically, and based on those patterns it's able to build its own opinion, its own, not opinion, but its own artificial thinking, basically, right? So let me give you an example. So we if you want AI to recognize, let's say, a tomato, right? So we show it hundreds and thousands of images of tomatoes, basically, until it's able to recognize any tomato image that we put in front of it, right? So that is kind of a manual simulated annealing method, and that's how you tweak your AIs and machine learning models to make them more accurate and actually be effective in actually doing something, basically. So now that we understand the applications, we need to understand why does it work basically. That's the big question here now. So the brilliance of simulated annealing lies in its ability to avoid local optima. Imagine climbing a hill. A simple greedy strategy might be to stop as soon as it finds its peak, right? But what if there's a taller peak nearby? Simulated annealing tackles this by occasionally allowing downhill moves early in the process. These bad moves might seem counterproductive, but they help explore the landscape better, ensuring you find the highest peak, the global optimum peak, basically. So instead of climbing a peak immediately and finding a much higher peak somewhere else and then declining and then climbing again, simulated annealing basically allows you to go downhill first early in the process to find the basically optimal peak first and then climbing basically. So that's why it's to find the global optimum solution basically in that scenario. So simulated, now that we understand that how why it works basically, we need to understand how does it work basically. So I'm not going to go into too much details here. I'm just going to give a quick breakdown here. So there's initialization of the process of simulated annealing, where we start with a random solution and a high temperature. By high temperature, I mean that we give it all the applicable parameters or commands, just like in the World War Warcraft example that I mentioned above, and then it tries everything and anything to come up with random solutions basically to build its data feed on that particular issue basically, and it's collecting enough data for it to now optimize for a more powerful or more better solution to that problem. And then we have step number 2, which is iteration. So in this step you need to understand there are 3 things for each step that you need to do. You need to slightly tweak your current solution every time, right? So you're coming up with these random solutions, right? So you have a random solution, then you realize, hey, like I tried to walk from A to B. I'm again coming back to the World of Warcraft example. I'm going to A to B, but during that process, I fell when I pressed I fell, or I went back, or I jumped 5 times, but I wasn't able to get to from A to B, which is like 5 steps away, right? So the problem is jumping is not the solution, or ducking is not the solution. Moving back is getting me away, and moving right is getting me also kind of away, and so on and so forth, right? So it slightly tweaks that solution based on eliminating certain possibilities every turn basically. It also calculates the energy or cost of the new solution basically. So I was giving the 5 steps example as the basic constraint, but let's presume there's no constraint, right? So it says that from A to B, there are 5 steps needed, right? If you go in a straight line, that's the most optimum solution. But it tries jumping first, it goes back, it goes right, then it steps, and with many different combinations, it reaches point B. But it realized that it is not a very efficient solution. So every solution, it reduces the cost or energy of the new solution for the next solution so that it becomes more optimized. And then it decides whether to accept or reject the new solution based on the probability that depends on their temperature basically. So after going through for every step going through this iteration process, then the 3rd step is basically the cooling process basically. It gradually lowers the temperature, reducing the chance of accepting worse solutions. And it's at the last step basically, which is stopping. It stops the system when the system has cooled and returns to the best solution basically. That's the point where you find the best solution. So the next part of this video is basically fun and analogies and visuals that we'll go over to basically hammer in this concept of simulated annealing. So let's make this vivid. Basic, picture yourself as a treasure hunter in a dark forest, right? The temperature is the courage to explore the risky paths basically. Early on, you stumble and fall a lot, but that's okay. You're exploring the forest right now as a treasure hunter, right? You can't find the treasure immediately. You need to move around, explore different areas of the forest. That's the only way you can find the treasure basically. As you get closer to the treasure, you slow down, cautiously avoid distractions, right? So the temperature is the closer you get to the treasure, you realize the temperature goes low because you're taking less risky paths because you're almost near. near to your destination. You avoid distractions because you need to get to that treasure as quickly as possible. Other people might be looking for it as well. So when and finally you strike gold, and your riskiness completely ends because now you have the treasure and you don't want to take any risk while you have so much gold in your hands, basically. So that's basically a quick, fun way to picture what simulated annealing process in AI is, basically. So now that we understand this, like with everything, we need to realize nothing is very, very easy or simple. Like there's no challenges at all. Every thing has some challenges. And of course, simulated annealing isn't perfect as well. So it requires careful tuning of the cooling schedule, basically how fast the temperature drops, right? It's not guaranteed to find the global optimum every time, but it's gets to pretty darn close to the global optimum, basically. So it's very difficult to find the global optimum, but it gets very darn close to the global optimum. And it can be very slow for large and complex problems. So if you have like I mentioned town planning earlier, so if you're planning your town for a small village of, let's say, 100 people, that might be very, very quick. But if you're planning for a city like let's say London or New York, which has millions of residents, now that's a very, very complex and a large problem, and it would take months, if not it would take days, if not months, to solve that problem. So let's wrap up, right? So basically, we need to understand why simulated annealing is hot in AI right now. Simulated annealing is a tool for the bold, basically. Those who dare to explore imperfect solutions to find the brilliance, basically. Whether you're optimizing a building layout, scheduling tasks, or designing the next AI revolution, simulated annealing helps you think smart and act smarter, basically. So as we take a step back into the real world, remember sometimes a little randomness and a lot of patience can go a long way. Keep exploring, keep learning, and may your algorithms always find the highest peaks. With that, let's wrap up. But before that, let me ask you, can you think of a real world problem where simulated annealing could help, basically? And what other areas of life could benefit from a touch of controlled randomness? Let's brainstorm together and let me know of your solutions in the comments below. Let's discuss those solutions. So, the solutions of these two questions, please let us know in the comments below. Discuss them with people in the comments below. And let's brainstorm together and get a better understanding of what simulated annealing is. With that, we're going to wrap up this video. Please and like and subscribe if you got any value in that. I'll sign off and see you in the next video. Thank you.